Hi, welcome to Chapter 2 of our Signals and Systems course, Mathematical Representation. The mathematical representation of signals in signal processing serves as a foundational framework for analyzing, designing, and implementing systems that can manipulate and interpret a vast array of information. In this chapter, we will delve into the various classifications that enable engineers and scientists to approach signal analysis with clarity and precision. As the name suggests, this classification is determined by whether or not the time axis is discrete, that means countable, or continuous. A continuous time signal will contain a value for all real numbers along the time axis. In contrast to this, a discrete time signal, often created by sampling a continuous signal, will only have values at equally spaced intervals along the time axis. The process of converting continuous time signals to discrete time signals is a critical operation in the field of digital signal processing and is commonly referred to as sampling. Sampling is the method by which continuous signals which exist at every instant in time are translated into discrete signals, which are defined at specific intervals. The most fundamental approach to sampling is the use of a sampler, which effectively picks out the value of the continuous signal at regular time intervals. This interval is known as the sampling period T of S, and its reciprocal is the sampling frequency Fs. The Nyquist-Shannon sampling theorem plays a pivotal role in determining the appropriate sampling frequency. It states that for a signal to be accurately reconstructed from its samples, it must be sampled at a rate at least twice the highest frequency component of the signal, known as the Nyquist rate. When the sampling frequency is below the Nyquist rate, an undesired effect known as aliasing occurs, where high-frequency components of the signal are misrepresented as low-frequency components in the sampled signal. To prevent this, an anti-aliasing filter is often applied before sampling, which attenuates the high-frequency components of the signal that are above half the sampling rate. Quantization is another process that follows sampling when converting a continuous time signal into a discrete valued signal suitable for digital representation. This process involves rounding the sampled values to a set of discrete levels, which can introduce a quantization error or noise. Lastly, the encoding of the quantized values into a digital form involves representing each discrete sample with a finite number of bits, determining the signal's bit depth and affecting the signal's dynamic range and resolution. Overall, the transformation from continuous time to discrete time involves careful consideration of the sampling rate, filtering, quantization, and encoding to ensure that the integrity and quality of the original signal are preserved as closely as possible within the constraints of the digital system. The difference between analog and digital is similar to the difference between continuous time and discrete time signals. However, in this case, the difference involves the values of the function. Analog corresponds to a continuous set of possible function values, while digital corresponds to a discrete set of possible function values. A common example of a digital signal is a binary sequence, where the values of the function can only be 1 or 0. Previous chapter we already talked about analog to digital and digital to analog converters. The history of these converters are intertwined with the evolution of digital electronics. Early forms of these converters emerged in the mid 20th century as the need to convert analog signals to digital for early computers and communication systems became apparent. The capabilities of these devices have grown exponentially alongside advancements in technology, from simple low-speed converters to high-speed, high-resolution devices. The capabilities of both converters have been enhanced by integrating them into larger systems on chips, SoCs, which include a processor, memory, and these converters all on a single chip. This integration has reduced costs and improved the performance of electronic systems by minimizing signal degradation and latency that can occur with the discrete components. The applications for both analog to digital converter and digital to analog converters are vast and varied, found in everything from mobile phones to medical instruments to industrial control systems. In each application, they serve the critical role of bridging the gap between the analog and digital worlds, allowing for the digitization of audio, video, temperature, pressure, and various other types of data. In the study of signals, distinguishing between periodic and aperiodic signals is essential to understand how they behave over time and how they can be processed and analyzed. Periodic signals are characterized by their repetitive nature. They complete a distinct pattern with a finite interval, which then repeats indefinitely over time. The fundamental period of these signals is the shortest duration over which the pattern completes one cycle. And this property is pivotal in analyzing systems that are designed to operate with regular cyclic inputs. We can define a periodic function through the following mathematical expression, where t can be any number and capital T is a positive constant. Fundamental period of a function, f of t, is the smallest value of capital T that still allows equation to be true. The analysis of periodic signals often employs the Fourier series, which decompose a periodic signal into a sum of sines and cosines with harmonically related frequencies. This method provides deep insights into the frequency components that make up the signal, which is crucial in understanding and designing systems like filters and oscillators that respond to specific frequency ranges. The classification of signals into causal, anti-causal, and non-causal categories is fundamental in signal processing and system analysis, offering insights into the time dependencies of signals and systems. This classification is particularly crucial in understanding the behavior of systems in response to different types of signals and in designing systems that operate in real time or predict future assets. Causal signals are those for which the value at any given time depends solely on present and past values but not on future values. In practical terms, causal signals represent real-world phenomena where the future cannot influence the present. For instance, the output of a microphone at any given moment is a result of sound waves that have reached it up until that point, not those that will arrive in the future. Causal signals are pervasive in real-world applications, and causal systems, which respond only to present and past inputs, are fundamental in engineering because they are implementable in real-world, real-time operations. Anti-causal signals, conversely, are defined such that their value at any time depends on only future values. While less intuitive and seldom encountered in physical systems due to their inherent non-realizability. Anti-causal behavior is a concept that finds utility in certain signal processing contexts, particularly in mathematical and theoretical models used for signal extrapolation and in some predictive algorithms where future states are estimated from known future conditions. Non-causal signals are those for which the value at any given time can depend on past, present, and future values. These signals are not bound by the time sequential cause and effect relationship that characterizes causal signals. Non-causal systems, which can process such signals, are not physically realizable in real time but are powerful conceptual tools in signal analysis and system design, especially in the context of digital signal processing, where entire signal sequences can be known a priori and processed in batch mode. In contrast, causal signals are signals that are zero for all negative time, while anti-causal are signals that are zero for all positive time. Non-causal signals are signals that have non-zero values in both positive and negative time. This classification is based on the symmetry, even versus odd, properties of signals concerning the time axis. Understanding these properties enables engineers and mathematicians to apply specific analytical techniques that can lead to more efficient computations and deeper insights into the behavior of signals and systems. Even signals are symmetric around the vertical axis, meaning that their shape remains unchanged if the time axis is flipped. Mathematically, a signal x of t is even if x of t is equal to x of minus t for all values of t. Cosine waves and constant signals are classic examples of even signals. This symmetry simplifies the Fourier series and Fourier transform analysis because even signals consist of cosine components in their Fourier representations, eliminating the sine terms which are inherently odd functions. This property can greatly reduce the computational complexity involved in signal processing tasks. Odd signals, on the other hand, exhibit antisymmetry around the vertical axis. This means that flipping the signal across the time axis results in the signal also being flipped in amplitude. Mathematically, A signal x of t is odd is if x of t is equal to minus x of minus t for all values of t. Sine waves are example of odd signals. Similar to even signals, the symmetry of odd signals lends itself to simplifications in signal processing, as an odd signal's Fourier representation will exclusively contain sine terms, omitting cosine terms due to their even nature. The concepts of even and odd signals have their root in the early development of mathematical analysis and have been applied to signal processing as the field has evolved. These properties are particularly useful in the analysis and design of linear time invariant LTI systems, where signals are often decomposed into their even and odd components to simplify the analysis. We will cover LTI systems in the following chapters. Deterministic versus random classification fundamentally impacts how signals are modeled, analyzed, and processed in various applications, ranging from communications to control systems and beyond. Deterministic signals are characterized by their predictability and exact reproducibility over time. For a given system, knowing the initial conditions and the precise mathematical description of the signal allows for the prediction of its future values at any point of time. Sinusoidal waves, square waves, and sawtooth waves are classical examples of deterministic signals, which find widespread use in electronic signal testing and modulation schemes due to predictable nature. The analysis of deterministic signals often involves techniques that leverage their mathematical properties for exact solutions, such as Fourier transform for frequency domain analysis and Laplace transform for system response analysis in control systems. Conversely, random signals, also known as stochastic signals, exhibit unpredictability and variability in their behavior over time. These signals cannot be precisely described by a single mathematical equation as their future values are uncertain. Instead, random signals are characterized by statistical properties such as mean, variance, power spectral density. Noise in electronic systems, fluctuations in financial markets, and variations in temperature over time are examples of random signals. The analysis of random signals requires probabilistic and statistical approaches, focusing on the estimation and prediction of statistical measures rather than exact feature values. Techniques such as correlation functions and spectral analysis plays an important role in understanding and processing random signals. A central concept in signal and system analysis is that of the transformation of a signal. For example, in an aircraft control system, signals corresponding to the actions of the pilot are transformed by electrical and mechanical control systems into changes in aircraft thrust or the position of aircraft control surfaces, such as the rudder or ailerons, which in turn are transformed through the dynamics and kinematics of the vehicle into changes in aircraft velocity and heading. Elementary variable transformations allow us to introduce several basic properties of signals and systems. A simple and very important transformation is the time shift. A second basic transformation of the time axis is that of time in reversal. For discrete time, a signal x of minus n is obtained from the signal x of n by a reflection about n is equal to 0 by reversing the signal. Similarly, for continuous time, the signal x of minus t is obtained from the signal x of t by a reflection about t is equal to 0. Thus, if x of t represents an audio tape recording, then x of minus t is the same tape recording played backward. Another important transformation is amplitude scaling. Amplitude scaling represents a fundamental operation that affects the magnitude of a signal without altering its temporal characteristics. This operation is applicable to both continuous time and discrete time signals, allowing for the adjustment of signal amplitude to meet specific requirements, such as system compatibility or dynamic range optimization. Mathematically, amplitude scaling is expressed through a scalar multiplication of the signal by a constant factor. For a continuous time signal x of t, the amplitude scaled version a of t can be described by the equation I of t is equal to a times x of t, where a is a non-zero scaling factor and t represents continuous time. This operation uniformly scales the amplitude of x of t at every point in time, effectively increasing and decreasing the signal's overall magnitude while preserving its original shape and temporal properties. Similarly, for discrete time signals, which are defined at discrete intervals and represented as x of n, amplitude scaling is achieved through the equation I of n is equal to a times x of n, where a is the scaling factor and n denotes the discrete time index. Just like in the continuous domain, this operation multiplies each sample of the discrete time signal x of n by a, scaling the signal's amplitude accordingly. The simplicity of this operation belies its significance in digital signal processing, where amplitude scaling is often utilized to adjust signal levels before digital to analog conversion, to normalize signals for comparison, or to prepare signals for further processing steps that may require specific amplitude ranges. Another transformation is that of time scaling. For continuous time signals, a signal x of t is scaled in time by multiplying the time variable by a positive constant b to produce x of b times t. A positive factor of b either expands or compresses the signal in time. B is greater than 1 or between 0 and 1. A discrete time sequence x of n is compressed in time by multiplying the index n by an integer k to produce the time-scaled sequence x of n times k. This operation extracts every kth sample of x of n, so intermediate samples are lost and naturally the sequence is shorter. This transformation is also called downsampling or decimation. The discrete time sequence x of n is expanded in time by dividing the index n by an integer m to produce the time-scale sequence x of n divided m. It's convenient that this operation specifies every m sample and intermediate samples must be synthesized with such interpolation algorithms. The sequence is longer after the transformation. This transformation is called upsampling or interpolation. An important class of signals that we will encounter frequently throughout this course is the class of periodic signals. A periodic continuous time signal x of t has the property that there is a positive value of t0 for which x of t is equal to x of t plus t0 for all values of t. T0 is the period of x of t in time. In this case, it's said that x of t is periodic with period t. Periodic continuous time signals arise in a variety of contexts. For example, the natural response of systems in which energy is conserved, such as ideal LC circuits without resistive energy dissipation and ideal mechanical systems without any fractional losses. They are periodic and compose some of the basic periodic signals. Similarly, a periodic discrete time signal has the property that there is a positive value of n0 for which x of n is equal to x of n plus capital N0 for all values of n. Capital N0 is the period of x of n in sample spacings. For both of continuous time and discrete time signals, the smallest t0 or n0 is called the fundamental period of the periodic signal. From the properties and examples provided so far, it's seen that signals may represent a broad variety of phenomena. In many, but not all applications, the signals are directly related to physical quantities capturing power and energy in a physical system. For example, if V of t or I of t are the voltage and current across a resistor with the resistance R, respectively, the instantaneous power is P of t equals V of t times I of t, which is equal to 1 over R times V of t squared. The total energy expanded over the time interval t1 to t2 is the integral from t1 to t2 of p of t dt equals the integral from t1 to t2 of 1 over r times v of t squared dt. And the average power over this time interval is 1 over t2 minus t1 times the integral from t1 to t2 of p of t dt equals 1 over t2 minus t1 times the integral from t1 to t2 of 1 over r times v of t squared dt. With this motivation, it's a common convention to use similar terminology for power and energy for any continuous time signal x of t or any discrete time signal x of n. In this case, total energy over the time interval t1 to t2 in a continuous time signal x of t is defined as the integral from t1 to t2 of the absolute value of x of t squared dt, where absolute value of x denotes the magnitude of the possibly complex number x. The time average power is obtained by dividing by the length t2 minus t1 of the time interval. So, total energy in a discrete time signal x of n over the time interval n1 to n2 is defined as the sum from n1 to n2 of the absolute value of x of n squared. For periodical signals, it's important to compute signal energy and power over one period. Then, the signal energy for a continuous time signal x of t can also be defined as follows. E sub x equals the limit as t goes to infinity of the integral from negative t to t of the absolute value of x of t squared dt. And similarly, a discrete time signal E sub x equals the limit as n goes to infinity of the sum from n equals negative n to n of the absolute value of x of n squared. The average of the signal energy over time is considered as signal power. In an analogous fashion, we can define the time average power over an infinite interval as P sub x equals the limit as t goes to infinity of 1 over 2 t times the integral from negative t to t of the absolute value of x of t squared dt, and P sub x equals the limit as n goes to infinity of 1 over 2 n plus 1 times the sum from n equals negative n to n of the absolute value of x of n squared in continuous time and discrete time respectively. Exponential and sinusoidal signals serve as basic building blocks from which we can construct many other signals. An exponential signal is given by x of t equals c times e to the sigma t, where c and sigma are in general complex numbers. Depending upon the values of these parameters, the complex exponential can exhibit several different characteristics. If sigma is less than 0, that is exponential decay. If sigma is greater than 0, this is exponential growth. A damped or growing sinusoidal is given by x of t equals e to the sigma t times cosine of omega t plus theta. If sigma is less than 0, a damped sinusoidal signal occurred. If sigma is greater than 0, growing sinusoidal is generated. Another important class of exponentials is obtained by constraining sigma to be purely imaginary. Such a case, a complex exponential signal is given by e to the power of sigma plus g omega t plus g theta equals e to the sigma t times the quantity cosine of omega t plus theta plus I times sine of omega t plus theta. In this case, exponential growth or decay is modulated by a complex sinusoidal signal. Another important characteristic signals for this course are sinusoidal signals. Sinusoidal signals, characterized by their smooth periodic oscillations, are a cornerstone in the study of signal processing due to their fundamental properties and presence in both natural and engineered systems. Mathematically, a sinusoidal signal can be represented as x of t equals a times cosine of omega t plus theta for continuous time signals, or x of n equals a times sine of 2p fnt plus theta for discrete time signals, where a denotes the amplitude, omega radian frequency, f is the frequency in hertz, theta the phase angle in radians, t the time in seconds, n the discrete time index, and t is the sampling period for discrete time signals. This form encapsulates the signal's periodic nature, exhibiting a repeated pattern over time, which makes it particularly valuable for analyzing systems that operate over continuous or discrete intervals. The parameters of amplitude, frequency, and phase angles provide a comprehensive description of the signal's characteristic, enabling precise control over its behavior. The significance of sinusoidal signals in context of signal processing education and application cannot be overstated. They serve not only as a fundamental building block for more complex signals, given that any periodic signal can be decomposed into a sum of sinusoids through Fourier analysis, but also as a basic input for testing and analyzing the behavior of LTI systems, linear time invariant systems. Sinusoids are uniquely stable under linear operations, meaning that the output of an LTI system to a sinusoidal input is itself a sinusoid at the same frequency, is possibly with altered amplitude and phase. This property simplifies the analysis of LTI systems considerably, allowing for the characterization of system behavior through its frequency response. Moreover, the practical applications of sinusoidal signals span across through its frequency response. They're from the modulation of signals in telecommunications, where they are used to carry information over distances. Their inherent simplicity and predictability make sinusoidal signals an indispensable tool in the engineer's toolkit, bridging theoretical concepts with real-world applications in signal processing. The unit impulse and unit step functions are fundamental concepts in the analysis of signals and systems, serving as basic building blocks for more complex functions and systems. The unit impulse function, often denoted as sigma of t, in delta of t in continuous time and delta of t in delta of n in discrete time systems. Uh, They are defined as an infinitely narrow pulse with unit area under the curve for continuous time and a value of 1 at n is equal to 0 and 0 otherwise for discrete time. Despite its simplicity, the unit impulse function plays a crucial role in system analysis. It particularly in characterizing the impulse response of linear time invariant systems, which in turn defines the system behavior. These impulse functions are used to model physical systems that act over short time intervals, such as a hammer blow or a bat hitting a ball exactly at t is equal to 2, for example, or a rapid charging of capacitor. The unit step function, denoted as u of t for continuous time and u of n for discrete time, represents a signal that switches from 0 to 1 at a specified point in time, usually at t is equal to 0 or n is equal to 0, and remains at 1 indefinitely. This function is instrumental in understanding system responses to sudden changes in input and serves as a foundation for modeling signals that exhibit a step-like progression over time. It's also known as Heaviside step function. These are discrete representations, by the way. The step function is a useful tool for testing and for defining other signals. For example, when different shifted versions of the step function are multiplied by other signals, one can select a certain portion of the signal and zero out the rest. You can see from the figure how to interpret different step functions to create customized signals. Continuous time and discrete time systems are classifications that reflect the nature of signals they process. Continuous time systems operate on signals that are defined at every instant in time, making them suitable for analog signals like audio recordings or radio waves. These systems are governed by differential equations and are characterized by their continuous input and output relationships. The analysis of continuous time systems often involves tools like Laplace transform to solve the governing differential equations and to understand the system behavior in frequency domain. Conversely, discrete time systems process signals that are defined at discrete intervals in time, making them ideal for digital signals, which are represented by sequences of numbers. These systems are analyzed using difference equations and tools such as Z-transform, which facilitates the examination of the system's properties and its response to inputs in the frequency domain. The digital nature of discrete time systems aligns well with modern computing technologies, allowing for the efficient processing, storage, and transmission of digital data. Systems often denoted by block diagrams. Lines with arrows denote signals, boxes denote systems. Arrows show input and outputs. These input signals can be manipulated as summing, difference, and multiplication. As well as input manipulation, systems can be interconnected to form new systems in cascade or sum parallel. Two systems can also be interconnected with a special form of connection, feedback. Understanding the distinctions between continuous time and discrete time systems is so important for designing and analyzing systems that accurately process, transmit, and interpret signals in various engineering applications. This knowledge enables the selection of appropriate system types and analytical methods to achieve desired outcomes in telecommunications, audio processing, video processing, control systems, and more in engineering systems. So this is the end of chapter 2. We are going to discuss LTI systems, system responses, and convolution in the following chapter. See you.